Hello and welcome to Math with Mrs. Becker. Today in calculus, we are going to finish up chapter 1 by doing the second part of chapter 1, section 8. Okay, what we're doing today, a lot of it, you guys, is really going to feel like just common sense. It's going to take things that we have worked through during chapter 1 and kind of tying it all together. So the book does give us some crazy formulas and whatnot. I really think that in order for this to make the most sense, we just jump in, okay? So let's go ahead and just look at an example and I can talk you through what they mean. So we're talking about production. Let the production function, P of X, give the number of units of goods produced. So what it equals, okay, so we have a function. What it equals is the number of goods produced. X is the units of labor. So for example, it might be how many hours people are working at a factory. So it's units of labor, okay? If 5,000 units of labor are currently employed, so this is the production, 5,000, so let's say that units are hours. So if there are 5,000 hours being employed, what they can produce is 300 goods, okay? Now this is a first derivative. Remember, a first derivative, that's your marginal. So this would be marginal production. That means currently, if they are making, or if they have 5,000 units of labor, if they increase that unit of labor to 1, or like 1 more, if you go up 1 more unit, this would be 5,001. You could produce 2 more of whatever it is that they're making. Okay, so that's the main thing here. When you're looking at the second part of 1.8, you're going to see things like interpret this. They just want to make sure that you know what different things mean. So this would be if 5,000, X is units of labor. Okay, so just to have this kind of make sense, we're going to say 5,000 hours are worked at this factory to produce something. If 5,000 units of labor are employed, then what? It equals 300. Well, that 300 is the number of goods. So if 5,000 units of labor are employed, 300 goods are produced. And that could be anything. They might be making pianos. They might be making cars. They might be making bow and arrows. We don't know. They didn't tell us that. They just said goods. Now interpret this. Remember, if you have a first derivative, that is marginal. So this is marginal production. What marginal means is if you increase whatever the variable is by 1. So this would mean if I go from 5,000 units of labor to 5,001 units of labor, because we're just increasing it by 1, if we go from the 5,000 to the 5,001, they can produce 2 additional, I'm missing letters here, additional units. Okay, so that's what that means. A first derivative is marginal. It means that you take your current level, increase it by 1. So we're going 5,000 to 5,001 units of labor. If that happens, this result is 2, which means they can produce 2 additional units. Okay, estimate the number of additional units if X is increased from 5,000 to 5,000.5. Well, you guys, here's the deal. If you go from 5,000 to 5,001, you get 2 additional units, okay? So they're saying, well, what if we can't afford to go to 5,001? What if we only go to 5,000.5? So 5,000 to 5,000.5, well, that's half of that change. So half of 2 is 1. So they would be able to make 1 additional unit. If they can increase their employment by 1 unit, they can get 2. But if they can only increase it by half of that, it would be half of the 2, which is 1. And this is what I mean by it's kind of common sense. As long as you understand what's going on, you just have to step back and ask yourself, okay, what do we know? What would this mean? Okay, let's go ahead. Estimate. So again, and this was estimate as well. Okay, so you're just taking your knowledge and trying to make a prediction and figure out what's happening. Estimate the change in the number of goods produced if X is decreased from 5,000 to 4,999. Okay, so if I look at this, 5,000 to 5,001, we went up 2 additional units. So again, I always start off and I write down, okay, what do I know? This is what I know. I know that if I go up 1, I go up 2 more units. Well, let's go down 1 then. So if I go 5,000 to 4,999, it's the same distance here. This just went up 1 unit of employment, so it went up 2 additional units. Well, if we drop 1 unit of employment, I think it's safe to say we're probably going down 2 additional units. You would actually have 2 units less because you're going the other way. So again, rather than increasing our labor so we get more units, if you decrease your labor the same amount, I would assume that you would decrease the amount of units the same amount of units as well. Okay, so just kind of thinking through the problem. Here's a whole nother question. Okay, so new idea. The total cost in thousands of dollars. It's always really important to make sure you read the directions so we know our labels. The total cost in $1,000 of producing X units of a certain commodity is this function. So this is the cost. Find the marginal cost. Marginal cost is the first derivative. 6 times 2 is 12. I would still have 1x plus, this is a 1. 1 times 2 is 2. There was only 1x, so when I reduce it, it's gone. The derivative of a 10 is 0. So here is the marginal cost function. Find the cost and the marginal cost when 10 units are produced. Well, if I want to find the cost, I have to go to the original because this is the cost function. So C of 10. 6 times 10 squared plus 2 times 10 plus 10. If I go ahead and calculate that, grab my calculator, it was way over by the board. Okay, 6 times 10 squared plus 2 times 10 plus 10. I get 630. It's in thousands. So if you produce 10 items, whatever it is you're creating, when you produce 10, this is how much money it costs the manufacturers. Now they need to know this type of thing so that way they know how to price it so they can make a profit. Okay, so we're kind of thinking business-like here. Marginal cost. Marginal cost, I go ahead and take my first derivative and I fill in a 10. 12 times 10 plus 2. Well, 12 times 10 is 120 plus 2 is 122. It's in thousands. So what this tells us is if you produce 10 units, it's costing you $630,000. If currently you're making 10, if you decide to make 1 more, the additional cost for that 11th item would be $122,000. Use marginal cost to approximate the cost of producing the 11th item. Well, that's exactly what this just was. Okay, so if they want to know what the total cost would be, let's say total for 11 items. This is the cost for just the 11th item. If all of a sudden they're like, hey, we can afford that, well, the cost for the first 10 is $630,000. The 11th item is $122,000. So your cost would now be $752,000 if you went ahead and produced 11 items. This is the total for 10. This is the total for just the 11th. If you want the total for all 11, you would add the 2. Use marginal cost, so that's the first derivative, to estimate the additional cost incurred if the production level is increased from 10 to 10.5. Okay, so if I go from 10 to 11, it's 122,000 because that's marginal cost, right? If this means you're going up 1 unit. Well, they're like, we don't know if we can actually go up 1 unit. What if we can only go half? So 10 to 10.5, well, it would be half of this. Because if I go up 1, it's 122,000. Half of that would be 61,000. So again, just making those connections. On the back, now this is kind of a skill that we want to be comfortable with. They're going to give us a scenario and then give us some sample questions. We're not solving anything. You just have to figure out, what would you do? Here's the different methods of things that we could do. We got to figure out what's going on, okay? So let F of T be the temperature in degrees Celsius. So F of T, that's your temperature. Let F of T be the temperature in degrees Celsius of a liquid at a time T. T is in hours. The rate of temperature change at time A has a value using the first derivative, because remember, the first derivative is a slope. Slope is a rate. Listed below are typical questions about F of T and its slope at various points. Match each equation with the proper method of solution. What is the temperature of the liquid after 6 hours? If you're looking for the temperature, it's going to be the original. So I am going to be using the F of T. T represents time in hours, so I know the time. So what I would be doing here is taking the original and plugging in 6. Where I see that is A. You're taking the original, plugging in 6. We're done with A. Next one. When is the temperature rising? That is a change. When is it rising at the rate of 6 degrees per hour? So you want to know the derivative. So it's going to be the derivative. You want to know when. So we're solving for T. When would it equal 6? Because it's rising, so it's positive. So when is the first derivative 6? Right here is what you would be doing. That is E. By how many degrees did the temperature rise during the first 6 hours? So it says, by how many degrees did the temperature rise during the first 6 hours? Well, you would find the temperature. How much did it rise between hour 0 and hour 6? So I could go ahead and fill in a 6 because it was rising, so this would be the larger number, minus what was the temperature at the beginning. So this would be F. When is the liquid's temperature only 6 degrees? Okay, so when is the temperature, not looking at the derivative, when is the temperature solving for T? When is it 6? So set F of T equal to 6, solve for T. That is B. Guys, we're getting down there. Okay, so we have A, E, F, and B done. Okay, next one. How fast? That's a rate. So right now, I know without a doubt it has to be a derivative. So right now, I can already be like, okay, I have 2 left that I've done this one. I have 2 left that I have not done. How fast? Fast is a rate, but let's make sure that we're good to go with the rest of it. How fast is the temperature of the liquid changing after 6 hours? So we want to know the rate. 6 hours, that's the time. So you'd find the derivative, fill in a 6. That is D. All of them have to be used once, so I can go ahead and be like, yo, that's C. But let's look at it. What is the average rate of increase? Average rate of change is that slope formula. So what they're doing here is taking the second x minus the first x over the second y minus the first y. Rather than just writing 6 minus 0, they just made the calculation and said 6. That average rate of change is the slope formula like we looked at the beginning of 1.8. So guys, we just finished chapter 1. We're done. There are 10 questions in the book that I think are really good for you to look at as far as matching equations with what would you do, matching those questions, going ahead using some of that common sense with marginal, knowing that marginal is a change of 1. Well, what if you could go up 2? Well, then you would double that amount. What if you can only go up half? You'd go ahead and take half of the marginal amount. So again, there's 10 questions just to kind of practice these skills, and you do have your chapter exam coming up. So please make sure that you are working on those book assignments. If you are going for the notebook turn-in, time and time again, go ahead. If you have 5 spare minutes, look through some of the notes from chapter 1 just to get yourself ready. Hope you had a great day. I'll talk to you soon.